My name is Christopher McClellan, and today I'm very excited to share my research on learning expert models for educationally relevant tasks using reinforcement learning. This is work conducted in collaboration with Adit Gupta. It's an exciting time to be doing AI research, and there have been a number of developments in reinforcement learning that have enabled AI models to do things that we used to only think that people could do. In this paper, we explore the use of proximal policy optimization, or PPO, a policy gradient approach that is a variant of advantage actor critic that has been successful across a broad range of tasks and domains. For example, a team of 5 PPO trained models were able to beat 5 human experts in Dota 2. Additionally, I was part of the DARPA Alpha Dogfight program where we used PPO to train models to fly a simulated F-16 in 1 versus 1 air combat. The final model that came out of this program was able to beat expert F-16 pilots in simulated VR dogfights. Despite this success, there's been surprisingly little work exploring the use of RL to learn models for the kinds of educationally relevant tasks that humans regularly engage in, for example, math or language learning tasks. Now, I don't mean that RL has not been used to support educational technology. In fact, there's been substantial work exploring the use of RL for optimizing instructional policies, such as determining which problem or instruction to provide a student next. Instead, what I mean is that there's been very little work training models to do the kinds of tasks that people do. For example, actually learning the fraction and multi-column arithmetic steps for the kinds of tutors shown here. Now, to set the context for this paper, I've done a lot of prior research on building computational models of learning within intelligent tutoring systems. In part of this work, I developed the apprentice learner architecture shown here, which can engage with tutoring systems to learn an expert model for a task from work examples and feedback provided by a human or a computational tutor. I've used apprentice models to author tutoring systems and to run simulated A/B experiments to cost-effectively test the pedagogical effectiveness of tutors before classroom deployments. When I've presented this work in the past, I've regularly received feedback that I should explore how my apprentice models compare to the state-of-the-art RL systems, such as PPO. This paper aims to investigate the application of PPO to educationally relevant tasks and to explore how PPO compares to my existing apprentice model. Now, it's quite easy to apply RL approaches to environments like Atari or StarCraft or even robotics tasks because there are a number of existing interfaces and simulators that researchers can use, such as OpenAI's GIM. However, no such interfaces exist for educationally relevant tasks like tutoring systems. To support the ability to interface RL models with tutoring system tasks, I created TutorGym, a platform for training agents such as apprentice and PPO agents on educational environments. This platform is open source and available for other researchers to use at tutorgym.ai. And it's built to use the same API as OpenAI's GIM, so it can be easily interfaced with existing reinforcement learning models. Currently, the system only supports the 2 tutoring tasks shown here, fractions and multi-column tutoring tasks, which are the tasks that I explored in this paper. However, we plan to expand it in the future to support more tasks and domains that will become available in the future. Now, while Atari and flying an F-16 seem like more complex tasks than tutoring environments, it turns out that mapping the tutoring system tasks into a representation that's compatible with RL approaches ended up being quite challenging. The main issue is that most of the tasks that RL is good at use relatively impoverished representations. First, most RL models used fixed-size input representations. Additionally, they have relatively simple action spaces with just a few actions like the Atari controller shown here, namely left, right, up, down, and whether you're hitting the button or not. In contrast, tutors have sparse logical state representations that are combinatorial in nature, and it's difficult to know the full space of features in advance. Also, the action spaces are much larger because agents can enter arbitrary values into tutor fields. For example, they might enter any natural number, making an infinite action space. To overcome these issues, I had to employ a number of tricks. The first trick was to create an online OneHot Encoder to map the logical representations from the tutor into fixed-length feature vectors. My encoder would always output a feature vector with a fixed pre-specified size, for example 5,000 features. Initially, all the features are output as 0. However, as the system encounters new attribute value pairs, it dynamically maps them to correspond to unused features within the vector. The end result is a lossless mapping from the logical representation to a fixed length feature vector that doesn't require knowing the full feature space in advance. Given this encoder, I created two PPO models to investigate different input and outputs for the RL approach. The first model, PPO number, uses the logical representation of the tutor directly. It uses my OneHot encoder to create the input vector, which is then passed to the PPO model. The model has two discrete action outputs. The first output selects a field in the tutor interface to update, and the second output selects a number to put into that field. The second model, PPO operator, uses a representation that is as close to the apprentice model as possible. Similar to apprentice, it augments the raw state representation with additional relational knowledge, such as adding features to denote when two fields are equal. We selected the relational knowledge for this step to be identical to the relational knowledge that's used by the apprentice agent. It then uses my OneHot encoder to translate this augmented representation into an input vector for processing by the PPO model. The model has 5 discrete action outputs. The first action selects a field to update. However, instead of choosing a number to put in this field, the second action selects an operator to apply, where the operators are the same as those that were available to the apprentice agent. Mainly, it has operators for copying, adding 2 numbers, subtracting 2 numbers, and so on. Finally, it has 3 additional action outputs that correspond to fields in the tutor that provide values that are the arguments to these operators. This table shows a summary of the size of the input and output representations for each model in each domain. What we can see here is that the models have relatively large action outputs. In the fractions case, the number of actions was so large for one of the outputs that I had trouble getting the PPO model to converge. So I had to create an easy version of the fractions tutor that only uses the numbers 1 through 5 in the numerator and denominator of the fractions problems. This yields a much simpler environment that only requires the model to input the numbers 1 through 50 into the answer fields. And as we can see in the second row, this greatly reduces the number of action outputs. Here are the results showing the performance of the different models in each environment on the log 10 scale. On the left, we can see that the apprentice model, shown here as AL in red, only requires about 10 examples to reach mastery in the fractions tutor. In contrast, the PPO operator requires approximately 3,000 examples, and the PPO number requires more than 10,000 examples on the easy version of the tutor. It never reached mastery within the normal version. On the right, we can see that the multi-column tutor is harder. It takes apprentice approximately 125 examples to reach mastery. In contrast, the PPO operator seems to level off without ever achieving mastery, and the PPO number model achieves mastery at around 10,000 examples. Now here are the key findings of our paper. First, the PPO model was able to achieve mastery at these educational tasks, suggesting that PPO is able to generalize from games and robotics tasks to tutor tasks. Second, PPO requires much more training than apprentice to achieve mastery. By comparing apprentice to the PPO operator model, which has the same built-in knowledge that apprentice has, we're able to show that it's not just the additional knowledge that apprentice has that gives it its advantage. Instead, we hypothesize that the key advantage of apprentice is that it decomposes the learning problem into simpler subproblems, and it uses a hybrid analytic statistical approach. Lastly, there was an interaction between the PPO representation and the task. Specifically, PPO operator performed better on the fractions task, whereas PPO number performed better on the multi-column task. This interaction suggests that PPO's performance is sensitive to the representation design, and that the representation needs to be tailored for each task. In conclusion, we created TutorGym, a novel platform for interfacing and testing RL models on educationally relevant tasks. We believe that there's a lot of opportunity to apply RL to improve education and educational technology, and we hope that this platform enables more RL research in this application area. Using this platform, we showed that RL models can be successfully applied to learn tutor tasks. However, RL models like PPO are still not as efficient as learning models based on humans, such as Apprentice. Therefore, we argue that more work is needed to better design representations and algorithms that have improved learning efficiency. Thank you.